Good afternoon, Hamilton, or good evening in Birmingham, or good morning if you're joining us from somewhere else in the world. It's really great to be here in Canada and speak as part of the Commonwealth Games Queen Baton Relay events. I'm David Hanna. I'm Professor of Hydrology and UNESCO Chair in Water Science at the University of Birmingham, and also the inaugural Director of the Birmingham Institute for Sustainability and Climate Action. So today, with colleagues from McMaster and from Birmingham, we're going to provide some perspectives on how we can and how we do collaborate across institutions to address some of the challenges related to water and sustainable development goals in a time of really unprecedented global change. I'm going to set the talk up by providing the wider context to the water crisis, the need for science to underpin water security and development, and to think about some of the grand challenges for water science and society. I'm also going to address why it's critical that we better understand watershed processes for planetary resilience and sustainable futures. We hope the presentation will provide a clear example of how we can leverage global partnership for sustainable development, which is recognized by Sustainable Development Goal number 17, which is the last, but absolutely not the least. So our water cycle is changing, and we're facing a water crisis due to three interacting factors that are exacerbated by human interference in the water cycle. 77% of the ice-free land has been converted or changed by people. Climate change is accelerating the water cycle, and water is really the climate connector by which many people feel the impacts of climate change. And people use water in different ways. The majority, 75% or thereabouts, for agriculture, use water for domestic and industrial purposes, blue water, and return grey water to the environment in a polluted form. Together, this creates a water crisis for society, for ecosystems, and for hydrology. So currently, we still have about 1.8 million deaths per year as a result of water pollution, and 4 billion people live with severe water scarcity, and 80% of the world lives in areas of high water risk. In terms of ecosystems, 70% of rivers and lakes and estuaries suffer from eutrophication, and we've had a reduction of 83% in aquatic biomass. And although forests get a lot of attention, wetlands are disappearing 3 times faster, as are saline lakes. There are also feedbacks and impacts on the hydrological cycle itself as a result of the water crisis, with groundwater depletion and pollution, weakening of continental moisture recycling, and more variable precipitation and evapotranspiration patterns. And the feedback in terms of the freshwater flux to the oceans is altering ocean circulation. When we're dealing with these issues around the water crisis, we're often dealing with so-called wicked problems. And these are wicked for a number of reasons, due to complexity and uncertainty or lack of understanding, due to a lack of data, and often because we are dealing with interconnected problems where solutions in one part can cause unintended problems and consequences elsewhere. But we're really often dealing with evolving and competing human needs and contested uses of water. So what I'd like to do in this talk is emphasize really the need for science, and specifically the need for evidence to make better decisions about adaptation to climate change and other impacts on the water environment. So I'm really pleased in that context that the need for science has been recognized by UNESCO's Intergovernmental Hydrology Programme, which is the equivalent of the IPCC for water, in that it's put right at the center the need for science for a water secure world in a changing environment. So this science, alongside better water governance, more inclusive water management, are absolutely critical to achieving Sustainable Development Goal number 6 around water and sanitation for all, and ultimately thinking about a water secure world and more resilient societies. So to aid this, the University of Birmingham are working with the UNESCO Chair in Water Science to connect up new knowledge generation, strengthen the link between science and policy, and support the development of capacity in individuals and institutions. And we're doing this at a range of scales, from local community scale all the way up to the global scale. So it's very much a connector between research, education, and society. A key part of this work is also international cooperation, and that's we can, in the sense that we can absolutely do more together. As a reminder of the importance of water, I mean, very significantly, the COVID-19 pandemic and indeed the climate emergency have provided wake-up calls for water security. Work that we did showed that over 40% of households were unable to wash their hands, which was really key to combating the COVID-19 pandemic the day before. And this shone a light on the need to think about water availability, issues around too much, too little water, around water quality, water that's too polluted, and water access, water that's too far away, which adds the human dimension. So in this context, both McMaster and Birmingham are working together to address three fundamental challenges for science and society. The first of these is the need to quantify hydrological fluxes, stores, and their interactions. So thinking about how precipitation, evaporation, river flows, frozen water, snow and ice, groundwater, and also plant water interactions all hook up. Secondly, to think about how we can unravel the multiple and synergistic drivers of change. And you can see in the diagram below, these relate to interactions between climate, the land surface, and human factors. How do we separate those? How do we understand what the key drivers are? And if we generate this knowledge about how the water cycle is changing and why it's changing, we can understand better the uncertainties about making predictions and projections for places and spaces that we don't have information for. And this is really key to underpinning sustainable water policies and adaptive management, which will have benefits for societies and for ecosystems. So we're going to use these three grand challenges to structure the rest of the talk. So after I've provided this introduction, we'll go to Carey, who will talk about quantifying changes. Then we'll move to Shasha, who will talk about understanding uncertainties. And lastly, Mike Waddington will talk about drivers of change and also provide a bit of a look to the future. So when we're thinking about the water cycle, we need to recognize that the water cycle is very interconnected. And we were one of the first authors. I thought it was nice in the context of the McMaster Birmingham link to show this diagram. We were one of the first authors to show what we call teleconnections in the hydrological cycle. Teleconnections in the atmosphere have been known for some time, how the atmosphere is connected, but we showed for the first time that there's connections in the water cycle, and that autumn river flows in Atlantic Canada could be linked several months later to river flow patterns in Northern Europe. And that provided us a source of potential predictability. I wanted to flag this because this is a really fantastic example of the importance of data sharing, and was only possible through UNESCO's International Hydrology Intergovernmental Hydrology Program, particularly the FRIEND Water Program, Flow Regimes for International Experimental and Network Data. Moving from observations to models, I wanted to highlight the importance of understanding land surface hydrological processes. So we've undertaken work using multi-model ensembles, where we take a whole bunch of climate models and run those through a whole bunch of hydrological models and look at changes, in this case, up to the end of the century in both high and low flows. What you can see in the top diagrams is that we've got changes in high flows days by 2100, particularly at high latitudes in sub-Saharan Africa, and changes in low flows, both of those increasing, where we've got hotspots of change around the Mediterranean, around Central and South America and sub-Saharan Africa, and in Australia. But what was really exciting about this work was we were also able to look at the different sources of uncertainty, and particularly look at the dominant uncertainty, either associated with the global climate models or associated with the global impact models. And if you look at the plots on the bottom, you can see for some of the areas that are showing the greatest change in the future, the greatest source of uncertainty is not which climate model you use, but which hydrological model you use, which pointed towards the importance of understanding land surface hydrological processes and the way in which they're implemented in models. This is shown perhaps more clearly in this diagram, where you've got hydrological years plotted up in each of the boxes, and as rows, different hydrological models, and as colored lines, inputs from different climate models. And what you can see here is there's much greater differences between the hydrological models than there is between the climate models for any one hydrological model, which indicates the importance, again, of understanding terrestrial processes. And in this case, really showed that if we're going to improve our understanding of how the water cycle is changing, we can invest activity in improving our climate models, but the biggest benefit might be in improving our way in which we represent processes within hydrological models. To further reinforce the importance of land surface processes and change, and particularly thinking about the interaction between water and vegetation, which is a major area of collaboration between McMaster and the University of Birmingham, we suggested that as the water cycle becomes more homogenized, we lose ecosystem resilience and hydrological resilience. So what you've got plotted up here on the left is a natural vegetated landscape and various hydrological fluxes through it in the blue. And what you can see is as you move from a mixed ecosystem to a monoculture, that the distribution of responses becomes much more constrained. And that limited response in terms of hydrology we hypothesize results in homogenization of the water cycle, less resilience of the system, and potentially greater potential to have shocks and to reduce the long-term sustainability of the system. So looking to the future, I'm thinking particularly about the area of ecohydrology, plant-water interactions. We really feel that there are some significant opportunities at this point in time to advance research and address some of these big challenges. What we've got plotted down on the bottom of the diagram are some of the opportunities we have to take the research forward by leveraging new technologies for sensing, new approaches to data analysis, including big data and machine learning, and being able to share data better and indeed engage communities in the collection of those data. Together, that should result in better interactions between our understanding of measurements, of models, and implementation of that into policy. If we look at the diagram on the top, you can see on the right-hand side a point on the roadmap of where we are now. We have lots of divergent routes, which we hope can bring together as a convergence of opportunities to advance understanding of, in this case, ecohydrological processes by better understanding of the processes, scaling, coupling and adding humans to the system, thinking about more dynamic models and how we can embed observations within them, and use measurements from new sensing technologies, as well as link practice and policy. Together, this should result in some improvements in fundamental science understanding, which will take us towards the left of the diagram and allow us to inform better and solve problems in the real world, which will take us on a route to improving global equality and justice and environmental sustainability. So I hope to have set the context there in terms of some of the grand challenges we've got for hydrological science. And I'm now going to, in the context of the Queen's Baton Relay, which has been at the McMaster University today, I'm going to hand the baton or the baton on to Sean Carey, colleague at McMaster, to talk about particularly the importance of data and observations.
Okay, hopefully I didn't drop the baton or baton. And thanks, David, for the handoff, and thanks for those who are listening today. It's been an exciting few days with the folks from Birmingham here. And I wanted to talk briefly about sort of my journey and the journey of some of us at McMaster and also at Birmingham and what we've been talking about, sort of the value of long-term data and experimental empirical data to guide policy and inform decision-making. So I think that we all live in an era of immediacy, and often in hydrology and in science, a lot of the funding is very much based on short-term election cycles, 4 or 5 year cycles, but the value of much longer-term observations is something that's becoming more and more important as we tackle some of these problems associated with global change. McMaster has always been a leader in long-term environmental observations. An example here is my colleague Altaf Rain has a number of flux towers at Turkey Point. They've been operational, I think, since 2001 or 2, and this is for forest management practices, carbon sequestration. My colleague, who will be speaking later, Dr. Waddington, works with indigenous communities in Georgian Bay, looking at sort of turtle habitats and snakes and wetlands and ecohydrology in a large number of ways. And this is an important way that we're working towards long-term observations and co-creation of data and information and knowledge with Canada's First Peoples. And that's something that McMaster is very sort of leading the way in, I think, in terms of understanding in our natural environment and basically looking at all the perspectives that Canadians have with regards to environmental change. Had to put this out for Altaf. Apparently one of McMaster's new environmental monitoring initiatives is the Carbon Sink Forest. I guess we're a finalist for the David Suzuki Future Ground Prize. Vote today. If you vote, we win. But really what I want to do is I want to bring you on a bit of a journey of mine. I've been working in Canada's north for approximately 30 years now, largely in the Yukon. And the one thing that we've noticed in that time is that there's been a rapid decline in observational capacity. There's been a rapid decline in our just sort of networks and in people working there. And so about a few years back, colleagues, some European colleagues and myself wrote these opinion pieces about how to save northern research and essentially really important value of long-term experimental data for hydrology and water management. And it's quite shocking how just collecting data on hydrology is a hard thing, and it's sort of what's actually guiding a lot of our information is by looking at data sets for many, many years. So my home away from McMaster or from Hamilton is this place in the Yukon. It's one of the most beautiful places. It's this Wolf Creek Research Basin. We're celebrating our 30th anniversary. It's just south of Whitehorse. If anyone is in the Yukon, August 3rd between 3 and 7 p.m., come to the campground. We have art, we have stories. We're going to do some stream gauging, but we're going to celebrate with all the partners and communities there what we've found over the past 30 years. Other places that I work are farther up in the Yukon. Here are some pictures of what it looks like, and you can see photos of me on the bottom from 1997 to 2002, all of which I am still smoking a pipe. And if there's any evidence of environmental change, it's certainly in the way I look. The top right photo would be me in 1996, I think. So there's been some changes in the natural environment and the human environment as well. By working in environments like this over very long periods of time, you can develop fairly deep relationships. We have a website, but we've also worked with artists, with musicians and other folks to sort of get our scientific message across. The art in this presentation is by a UK-based artist, Gennady Ivanov, and who's been to the Yukon a number of times and painted pictures of our catchments and tried to translate our research into science. Second place that I want to talk to you just briefly about is an even more beautiful place probably is the Tombstone Waters Observatory, which was set up in collaboration with the Transatlantic First Nation to answer some of the concerns they had with water in their traditional territories. So I don't need to mention to anyone that the world is warming fast, faster than anywhere on Earth. And in the Yukon, it's probably one of the fastest places on the planet. We've had observational increases in temperatures of several degrees since the 1950s that are having fairly large impacts on the landscape. The one that we hear most often about in the news is this idea of permafrost thaw. Permafrost is ground that's permanently frozen for a number of years. It's rock, it's water, it's all sorts of things. And if you look on the map, you can see Wolf Creek and the Tombstone Observatory, and they're at sort of the margin of where this is occurring. So over the past 30 years, there's been, the ground has moved towards 0 degrees Celsius, and there's been a large widespread thawing of permafrost. And this is kind of observed across the Pan-Arctic. And just to keep it simple, really what happens when you remove permafrost is you allow water to interact with materials that were previously frozen. So material where water couldn't flow before, it could flow now. So we're changing the hydrological regime, we change the chemical regime, we change the biogeochemical regime, and there's all sorts of kind of knock-on consequences. The consequences that we are able to describe and understand are simply because we were observing these systems before. Many people have heard of the carbon bomb, which is this release of methane from oxidation of frozen permafrost. This is Gennady's interpretation of it. But really, one of the big things that we've discovered in the past few years is that Canada's critical infrastructure is really at risk because of changing environment, and particularly climate change. This is a photo of the Dempster Highway. It's Canada's most northerly corridor. I guess the Inuvik Highway now is the most northerly one. It's a beautiful spot, traverses through several mountain ranges. And since 2005, the road has cost $500,000 a year, per year, more to maintain. So that's millions of dollars more each year that this highway is basically cost. And the reason of this is climate change. We've thawed permafrost, so when previously we didn't have water flowing beneath the ground, it is. We have rainstorms that didn't occur before, and it's causing all sorts of infrastructure issues along this highway. There are trucks that drive up and down this highway continuously. There are a number of camps just to keep it open. What you're seeing on the left is groundwater discharge. It's called icing. That didn't occur previously to the extent that it's doing now because of this thawing permafrost. This is a photo we put together, and it pictures with 1,000 words. These culverts are supposed to what keeps the highway safe as it's freezing through the winter. You can see the temperature on the top right. It's well below zero. It's going to get to -30, and you're going to see water being squeezed out of the ground into the culvert and completely close the culvert. You completely close the culvert, it's -20, it's -30, it's closing, it's closing, it's closing, it's closed. What happens when the snow melts? The road disappears. Fixing these roads is a Canadian problem. This happens all, in sort of other places of the world, a direct result of climate change. So yeah, here's just some photos of it. These are supposed to be empty, they're not. So this is something that we've seen. 20 years ago, these processes didn't occur to the extent they do now. And this is sort of something that we will have to adapt to. The other one that's rapidly occurring, that's observed across the Arctic, is kind of a funny story for us, is this rapid greening, which has sort of very strong effects on the water cycle because it impacts the amount of snow that traps. It's enhances the amount of evapotranspiration occurs. And I have a PhD student, she's spending a lot of time trying to understand how trees and shrubs affect these things. It's a very eco-hydrological study, and it really shows how just the immediate effects of climate change can have really strong effects on the water cycle that we didn't anticipate. Most people talk about permafrost thaw, but changing vegetation is a rapid and sort of kind of shocking influence on the water cycle. These are, when we set up this site, it was actually in the 90s, we didn't realize shrubs grew, and all the sites that we instrumented, every year we were wondering why we put the instruments where they were, but it was because the vegetation was growing. We weren't obviously working with ecologists at the time and didn't think the vegetation would grow. But now that there's this vegetation that far exceed our instruments, and we actually leave the instruments there as historical monuments to our sort of foolishness. And so Gennady came and painted pictures of the flames and the shrubs kind of exceeding the tower and making it useless. So we've seen, what have we learned? We've learned that the weather is changing. There's less snowpacks, there's changing precipitation, there's changing this chemistry. We have 30 years of data. This is the second longest data set in Canada, but there's only 2 that really occur that long in the entire Arctic. We know very little about our environment, and being able to talk to governments and officials to keep these sort of long-term data streams going is very, very difficult, and one of our actually grand challenges in hydrology. It perhaps is a wicked problem, continuing these observations. People talk very much about climate. In Canada and elsewhere in the world, resource extraction is becoming more and more, whether it's minerals, whether it's oil, et cetera, across Canada's north. There's trillions of dollars in liability, if not more. On the left is a picture, a Google Earth GIF I put together of the oil sands, where a lot of people at McMaster have worked in the past, showing the evidence of mining since 1984. This is a very, very large area. This is 900 square kilometers of impact. On the right is a former postdoc of mine, Claire Oswald, who's now a professor at Toronto Central Technical, Toronto University, the new one. And but we do a lot of sort of building back better, perhaps, at McMaster. And I know Birmingham is very interested in this work as well. And they do a lot of work with their own long-term observatory. So this is a real exciting collaboration. So finally, my final words: science, communication, knowledge mobilization, and co-creation really only happens through long-term relationships. Only through long-term relationships are we able to speak to the public, engage people other than scientists who really have a lot of agency in the work and previously haven't got agency or don't get agency when you're doing very short-term research. So the most important thing in science, I always tell my students, they always ask and they always think it's, I don't know, the ability to code or something like that. But I always say it's relationships and communications, and relationships are built through long-term observations and long-term commitment to science, which is, again, becoming harder and harder. After a while, every once in a while, they'll name a beer after your research watershed. That only takes about 30 years, or at least a flight. And in sort of these long-term commitments, I think there's Greta Thunberg on the bottom right. She's retired now. I'm 1 degree of separation away from her, from my colleague, John Pomeroy. These things take a long time to get this level of interest in hydrology and water science. And it's something that I think hydrologists is a grand challenge, is public engagements and relationships under the threat of climate change, because the climate crisis is a water crisis. So with that, I'm going to pass it over to an old student here at McMaster and friend of mine, Shasha Han, who's going to talk about the work she's doing at Birmingham as a new professor. So Shasha, welcome to the camera. Pass the baton.
Okay, so to address the grand challenge, as David mentioned, as understanding uncertainty on prediction, we did some work on probabilistic flood forecasting. We integrate a Bayesian ensemble uncertainty processor with the ensemble weather forecast. So Bayesian ensemble uncertainty processor is a Bayesian system, so it updates prior distribution into posterior distribution by assimilating all the available information at the forecast time. So it considers all the uncertainties related to the model, such as model parameter uncertainty, model structure uncertainty. And the ensemble weather forecast, it considers all the uncertainties on the meteorological inputs. We found by integrating those 2 components together, it produced improved probabilistic flood forecast in terms of reliability and accuracy based on various of metrics such as CRPS, reliability plot, and the scatter plot, where we compare the probabilistic mean with the observations. And here is one example of the forecast hydrograph. Here is we stand at June 27 and then forecast for 3 days ahead. And as we can see from the figure, it's the probabilistic forecast generated by the system not only gave 1 point forecast, but also has the associated uncertainty. And the uncertain bound captured the observed river discharge very well. And here is another work on understanding the uncertainty in probabilistic flood plan mapping and the changing climate. So we use HackMath for hydraulic model, which feed by the ensemble climate projection, and then use HackRes for hydraulic modeling. And then the flood map were further analyzed using ArcGIS. And as we can see the figure here, it's an example of the probabilistic flood plan map and the different climate change scenarios. And the blue gradient means the flooding probability. And the simulation results indicate an increase, not only the increased flood inundation area, but also the increased river flow depths. For example, for the watershed that we are working on, it's a small Canadian watershed with a drainage area of 77 square kilometers. We find under the high emission scenarios, under 2050, the projected flooding area could increase by 1.7 square kilometers. So the large associated uncertainty plus the increased future flooding risk and the climate change indicate a great need for enhanced flood modeling techniques and tools, and also indicate a great need for improved flood management capacity and a crucial need for enhanced resilience to climate change and long-term sustainable development for the watershed. And here is another piece of work trying to investigate the drivers of the flow change. The figure shows the changes in river flow across the UK. We can see in the UK, it's broadly indicate increase in the southwest part and the mix of increase and decrease in the northeast part. There are many research literature work on climate change studies, but whether we can take future climate-driven river flow projection at the face value, or whether we may be missing some key drivers of non-stationary river flow, some local catchment-specific drivers also play a very important role, such as urbanization. And to investigate the impact of urbanization on river flow, we applied a very strict catchment selection criteria. So we finally have 12 catchments which have experienced both flow change and also significant urbanization change. And this figure shows the distribution of the urban coefficient for different seasons and flow quantiles for our study catchments. And the urban coefficient tells for 1% of urban land cover change, how much does river flow change? And the result indicates urbanization effect varies considerably across catchments, depending on the seasons, the flow quantiles, and the geology. Like Tolston is like unhappy family. All the families are all alike, but each unhappy family is unhappy in its own way. Similarly, each urban catchment is urbanized in its own way, but the results broadly indicate an increasing effect of urbanization on river discharge. And the catchment variation of urbanization effect indicates we see a strong urbanization flow signal in catchments with less initial urban extent and low bedrock permeability, which indicate when we forecasting or projecting the future river flow, we need to be particularly cautious for the catchment, which is less urbanized now, but is likely to see rapid urbanization in the near future. And based on this work, we do further work on projecting stream flow and changing climate and urban land cover. So we use the same study catchment and the same methodology, but feed the model with the projections of climate and urbanization. Here, the figure shows an example of the probabilistic projection of future mean flow in summer. And the purple one is for changeable scenarios. as we can find, there is a significant increasing effect on the stream flow, but with considerable uncertainty. So all those work linked back to the sustainable need for our watershed. And those are some of our research work. Now I will hand back the baton to our McMaster colleague, Mac.
Great, thank you very much. I guess I'm in the final stretch on the last leg of this this relay. I'm Mike Waddington. I'm the Canada Research Chair of Ecohydrology here at McMaster University, and I've chosen this slide as an important one. In very much this discussions between McMaster and Birmingham today have been in 10 years in the making. I was very fortunate to attend Birmingham as a Penman lecturer in 2012. We've had discussions ever since, and this aspect of unraveling multiple and synergistic drivers of change is a really important question. Dr. Sophie Wilkinson, former postdoc here at McMaster, and Nick Kettridge at Birmingham have shown that when you combine climate and land use change can result in threshold changes in how ecosystems function, very much controlled by hydrology. This photo here is from the 2016 Fort McMurray fire, and this is a wetland south of town. That was actually where the main evacuation of 80,000 people took place. And this fire actually took over 400 days to put out, in part because of the land use change and fire combining. This wetland in itself lost over 2,000 years worth of carbon accumulation. So breaking apart these drivers are going to be incredibly important, especially if we put it within a ecohydrological lens perspective. This is some great work that Francois Rubin, a former postdoc within the Boreal Water Futures Program, which was led out of here at McMaster, illustrating the different socio-ecological systems on the left and different drivers of change, and that these drivers occur over a variety of different timescales. Some can be policy driven, some are economic. Of course, we have the physical that we've talked about. And then these then transform through the watershed through changes in different terrestrial processes, hydrological, in-stream processes, changes in storage, which have implications for biodiversity, water quality, water quantity, and timing. It's also a spatial problem. Here, just choosing Canada as an example of the Boreal and Western Cordillera. Here we have forest disturbance from 1985 to 2010 in Canada. The red are fire, the black is harvesting. And you can see that a tremendous amount of Canada's forest systems and therefore watersheds are impacted by these disturbances. But then a lot of these disturbances, such as in areas of northern Alberta, in Quebec, you also have the multiplicative impacts of these multiple drivers. In Canada alone, we about 1.5 million hectares a year are burned and over 1 million hectares are harvested, and has now result in watersheds with a variety of different stand ages and so on, which have knock-on effects for the hydrology of these watersheds. As Sean showed earlier, the strophification or the greening of the subarctic is quite important. But what we're also seeing is we look at this graph of mean annual temperature versus precipitation across some of the key biomes in Canada, is that you're getting a lot of changes, particularly at the edges of the bioclimatic envelopes. And that could have very large effects on the storage and fluxes of water, but also that the signs of those changes are not the same. We're seeing greening in some areas, but we're also seeing a browning or the dieback of vegetation, which leads to the potential for novel ecosystems, changes in vegetation trajectory, changes in evapotranspiration, and therefore stream flow and water storage. Some of the early discussions that we've had between Birmingham and McMaster is that perhaps the existing paradigm of where we protect and maintain water resources through land management may be a time for a new paradigm. That time may have ended. Instead, we need to look at these building a more resilient watershed society interface by enhancing watershed resilience. And we're exploring right now this week on a potential way of building back better. And what does that mean by building and back and better? The issue is that increasingly land managers are being forced to be reactive, responding to not only water resource land management, but also unanticipated impacts on ecosystems as well. such as wildfire, where the water quality and the quantity can change dramatically and go through a transformative change. As an eco-hydrologist, I see this challenge through that lens. And as a result, I think we need to have an approach where we take an integrative land and water management approach from a socio-ecological systems perspective. So we're really excited here this week to be able to announce that Birmingham McMaster researchers are partnering to tackle some of these challenges. We're looking to leverage our expertise in skills facility, experimental forests as BIFOR in Birmingham, our water observatories such as we have here in Canada, and to co-develop the next generation of climate and water scientists to take on some of these really important United Nations Sustainable Development Goals. Indeed, water applies across all 17 Sustainable Development Goals, and McMaster and Birmingham are committed in developing the next generation of scientists. This is a perfect time, and I'll finish with this slide here as the final stretch of this 400-meter sprint is in sight, in that we're now in the United Nations, we're 2 years into the United Nations decade on ecosystem restoration. Here at McMaster, we are known for our international medicine program and evidence-based medicine and problem-based learning. And here on the West Campus, we're looking to potentially return a parking lot back to a wetland and as a way to enhance watershed ecosystem restoration. And we'll be doing a tour of that facility tomorrow with our Birmingham partners. So with that, I'm going to cross the finish line and finish there, and be happy to take any questions at this time.